Okay, yeah, so how do we do this, right? So, quick review. What we said, remember we talked about, I can't remember, Thursday, Friday, something like that. We talked about using differentials to do quick estimations of you know, most likely thing we're going to be doing is calculating propagated error. Say it again. Oh, what the answer is? Okay, so let's get the bottom of this in. So if we want to do something like this, we want to estimate a square root of 98. We're going to use the trick that we talked about last week. Remember what that trick was? We said that we can approximate that the actual change in a function, and we drew a picture for this. I probably should have pulled up that picture, but remember what the picture looked like. We just said, I'll sketch it and then erase it here. So we had some function, and if we're going to move over from x, some distance delta x, then the function actually changes by an amount that we might call delta y, right? But we can estimate that with the differential dy. Okay, and if you ever forget what dy is, you don't even hardly have to think about what it is because it's so easy to derive this formula. It just comes from the fact that the derivative, or this is a way to remember it at least, that the derivative can be written, if you write a derivative equation where you've got the differential form of a derivative equals the function form of a derivative, and solve for dy, right? If I solve for dy, I'm just multiplying both sides by dx, and so the estimated, or the approximate change in the function is just going to be the derivative times dx, which is how much we're deviating from our comfortable, measured, convenient x value, right? In this case, how's that going to work? What do you think is going to be, so if this is our formula, we need to know a couple things here, don't we? We need to know what x is for our situation here, and we need to know what f of x is, and we need to know what dx is. Well, let's start with the function. What's f of x for this case right here? Well, okay, square root of 98, now that's a number, but what's the function going to be? We're taking square root of x. Okay, so we've got this f of x is the square root of x. What is x going to be? Not exactly. X is going to be, now x is going to be 100 because that's, remember, x is going to be the, in the case that we're doing propagated error, we said that x was the measured amount, and then there was some error in the measurement that could cause us to budge from that x value, right? Remember, we did, and we looked at an example, we looked at a couple examples, but I think they were both volume examples, where we had something like v of x equals, I think you guys did this one to kind of finish things up, v of x equals x cubed, and we measure, x was like, I think it was 10.1, wasn't it? Plus or minus 0.1, something like that. Inches, centimeters, doesn't matter, something like that. And then we said that dv is approximately equal to d prime of x dx, right? Where this is our x value, and this was dx, right? Remember that stuff? And we said then if this is v of x and this is v prime of x, then dv is equal to, 3x squared dx, right? And then we could plug that stuff in. We could plug in 3 times 10.1 squared times plus or minus 0.1, and that's going to give us the plus or minus value that we're going to get for our error calculation, the propagated error. Now, more often than not, when we're doing problems like that, remember, what we really wanted to find was a relative error. And we said we want to know as a percentage, what is the propagated error relative to the calculated volume? So we said dv over v, and we got the answer 3x squared dx over x cubed, right? Instead of just plugging numbers in, we're able to algebraically cancel a bunch of stuff there, right? And get 3 dx over x, and then we got our answer, right? Well, what was our answer? Our relative error, I guess, was 3 times plus or minus 0.1 is plus or minus 0.3 over 10.1. What do we get for an answer? I mean, something, you know, we got plus or minus some percentage on that, right? Okay, this one over here, slightly different, right? But x in this case, rather than being the measured value, is going to be the convenient value of x. And being as we've got a square root function, you know, 100 is a convenient value because it's a perfect square, right? That's one we can calculate in our head pretty easily. So we want to pick x to be that, right? Now the deviation from x, from 100, is going to be this part right here. So that's going to be our dx, right? See how that works? And so if we do that, then we got f of x is square root of x is 100, dx is negative 2, right? And we could say then that dy, in this case, is equal to, what is the square root of, or excuse me, what is f prime of x? Well, we'll see. Yeah, we'd have to do a little calculus there, wouldn't we? This is getting kind of messy. Let me, I gotta coordinate this part off here. It's kind of, there, that's separate stuff. So we know that if f of x is x to the 1/2, whoops, then f prime of x would be 1/2 x to the minus 1/2. Isn't that the same thing as just saying 1 over 2 times x to the 1/2, which is just 2 times the square root of x on the bottom, right? Okay, so then dy is equal to this, 1 over 2 times the square root of x times dx. Well, x was 100, dx was negative 2, right? So that's just negative 2 over 2 times the square root of 100, right? So that's, yeah, those cancel, right? I just get negative 1/10. Right? Okay. So how does that help us? Well, here's how that helps us, because we know that, oh, what is that? The f of x plus dx, which is f of 100, right? Isn't that f of f of 98, sorry, f of 100 minus 2, there's our f of 98, is roughly equal to, that's roughly equal to f of x plus dy if we use our differential, right? And that's from the picture that we drew the other day. Right, we said that that's x, and that's x plus dx, because this distance is dx. If I want to know the value right there, right, that's the same thing as saying y plus what we're estimating to be dy, okay? And so here's how we get to do this then. If that's true, then this is roughly equal to f of 100 plus what we just calculated, right, dy, which was this, negative 0.1. Okay. Plus f prime of 100, well, let's write it as dy. So that's about the same thing as saying the square root of 100 minus 0.1. 10 minus 0.1, about 9.9. How close are we? Yeah, pretty close. Right, pretty close. Okay, try another one. See if you can just, let's do just a couple of these. So make sure you get this down. Because this is a pretty easy way to do it. What if I want to estimate, let's say, the square root of 66? What's that going to be? We're going to estimate that as the square root of what plus or minus what? Okay. So that's the same thing as saying the square root of 64 plus 2. Okay? Right? Okay, and we know that, just like before, right, we know that f of x plus dx is estimated by f of x plus dy. Right? So x is what? 64. Dx is positive 2 this time, right? And our function is just a square root function, right? And so just like before, we got the answer. F prime is just 1 over 2 times the square root of x, right? So dy is just f prime of x dx. Right? Okay, so we can get our answer pretty easily. So our answer is roughly equal to f of x, square root of x, plus dy dx over 2 square roots of x. X is 64, dx is 2. We can just about do that in our head. We really think about it. It's a little early for that. You guys, oh my gosh, there's time warp. Look at that. So square root of 64 plus, what do we get? 2 over 2 times the square root of 64. So what's that equal to? 8 plus 1/8. 8 and 1/8. Okay. Yeah, 8.125. Pretty close. Try one more of those. You guys try one here. We'll give you a little different one though. How about let's estimate the cube root of.
Can't do that to us.
Oh, sure.
We don't know what we're doing yet. We're lost.
The cube root of 122. Try that. Okay, so what's our function here?
125. Or 180.
Okay, but what's f of x, I guess?
It's a cube.
Cube root of x.
Cube root of x, right? We're doing a cube root of a number, right?
Yep.
So f of x is just x to the 1/3. So what does that make f prime of x? Okay, so 1/3 x to the negative 2/3. Now that 2/3 seems a little weird, but don't. How do we think of x to the 2/3? Cube root of x squared. Yeah. Okay. So we could even write this if we wanted to as 1 over 3 times the cube root of x squared. Right? What's x? Or x is the convenient value, right? So what's x? 125, a perfect cube, which makes dx negative 3. Good. Okay. Right. So then if we plug all this stuff in, f of 125 minus 3 is roughly equal to f of 125 plus 1 over 3 times the cube root of 125 squared times, whoops, I forgot my dx, didn't I? Oh no, that's it, times dx. And then dx is our negative 3. So, cube root of 125 minus, in this case, 3 over 3 times the cube root of 125 squared. Yeah, we get good cancellation. Cube root of 125 just gives us our 5. The 3's cancel. What's the cube root of 125? 5 squared. So we got it. 5 minus 125. Doesn't make a difference. No. It's actually it's better. I mean, I retract that. It does make a little bit of difference. It's easier for us to think of it as not being on the inside, because if it were on the inside, that'd be kind of tough. I got to do the number 125 squared. Yikes! Then take a cube root of that. So, and this illustrates kind of a general principle. When you're doing stuff, when you're doing any kind of arithmetic operation where you're not doing functional stuff, you're just trying to calculate a number, you always want to try to, if you've got a composition of different stuff that you're doing, strategically, you always want to make things smaller before you make them bigger. Another classic example, like if I were going to, just to illustrate that point, it's just kind of a good thing to remember in math. Like if I wanted to, for example, distribute 5 over the, say I'm distributing 25 over the fraction 7/5, right? I got some options here because I've got really a combination of 3 operations. I'm multiplying and I'm dividing, or 2 operations, I guess, right? Which one do I want to do first? Do I want to straight distribute the 25 and get 25 times 7 divided by 5? No, not in this case, right? I'd rather reduce first, because you see what I'm saying? 25 over 5 reduces to 5 over 1. And then 5 times 7 is just 35, much easier, right? Okay. All right, they do, if you want to have a little closer look at this, they do go through a good example in the textbook, too, of how you can do the estimation. And we did all radicals, but you can do the same thing. We could have done the same thing with squaring something. It doesn't make any difference. I mean, if I wanted you to square, for example, estimate the square of 5.1 squared, I could do the same thing. What would my function be there? X squared, good. What would the value of x be? Well, 5, right? Because we know what 5 squared is, and then dx would be 0.1. You could do it that way too. Okay. All right. I didn't mean for that to take too much time there. How about if we